start 2-2 today. We're going to go up through the first 3 pages of 2-2. So we're going to get all the way, hopefully this is my plan, to get all the way up to here, so, which is on page 3 of Infinite Limits. So that's my goal. All right, here we go. Are you ready? Today, oops, where's my pencil? All right, today's May 8th. And we are finishing up section 2.1, which is the rates of change in limits. So our last thing about limits that we have to talk about today is the sandwich or the squeeze theorem. And what this sandwich or squeeze theorem does is that it finds the limit of ugly functions. Things that you would not be able to find the limit of, that you can't factor, you can't rationalize the denominator. It's not a trig that you can work around with some of those ones that we memorized yesterday. So we kind of got to go, yeah. It sounds very, very confusing, but once we draw the picture, it won't be so bad. All right, so here we go. If g of x is less than or equal to f of x, which is less than or equal to h of x, for all x not equal to c in some interval about c, and if the limit as x approaches c of g of x is L, and the limit of h of x as x approaches c is L, then by, of course, the limit as x approaches c of f of x is also L. Got it? Yeah. Okay, no, doesn't make a bit of sense, and that's totally okay. All right, so we've got this relationship going on between these 3 functions. G is less than or equal to f, which is less than or equal to h, everywhere for x not equal to c. So we've got some c value going on in here, okay, in some interval around c. So we're going to be looking at some interval around c. All right, now, g of x is smaller than f of x is smaller than h of x. G of x, and you're probably going to want like 3 colored pencils here, 3 different colors. G of x is some nice function that you can find the limit of. So let's put some g of x here. It is some nice function. H of x is also a nice function. And h might be something like that. Bless you. Okay, why did I draw it this way, and why did I have these 2 kind of almost meet right here? And that's because these conditions were set up. The limit as x approaches c of g of x is equal to L. So here's g of x. The limit as x approaches c is that height, L. Also, the limit as x approaches c of h, of this other nice one, that limit is also L. And would you agree with me by looking at these 2 functions? They both, as x approaches c, they both approach that particular y value of L? Do you agree? Nod your heads. Yeah? Okay, everybody see it? All right, now, f of x is our ugly function. That's the limit that we're trying to figure out. Can you see that green? I'm going to use a darker green. Where's f of x in relationship to g of x and h of x? It's right in between them, right? F of x is in between g and h. So let's draw some f of x. No idea what it's doing, but it's a function. Oh, look what's happening. Do you see that f of x has to squeeze in between h and g? So if we know that the limit of this lower function, if you will, is the same as x approaches c as the limit of this upper function, and any function that's sitting in between them then also has to have the same limit as x approaches c. Visually, can you see it? Yeah? All right, let's take a look at an example and see how we work through this example. I want you to find the limit as x approaches 0 of x squared times the sine of 1 over x. Okay, what happens when you try and substitute in a 0? We get something that's undefined. Yeah? Okay, so that's a problem. So we're kind of in trouble. I can't factor the sine of 1 over x. That's not giving me any of the trig ones that we memorized from yesterday. Oops. This is our ugly function. And I have to try and trap that ugly function in between two nice functions that I can figure out the limit for. All right, would you agree with me that the sine of anything from the unit circle must be between -1 and 1? Agree? Y values off the unit circle, sine has to be between -1 and 1. Well then, the sine of 1 over x has to be between -1 and 1. And now what I'm trying to do is to go through some legal mathematical steps to try and generate this function. And I want to get that thing sitting in the middle. Well, I have sine of 1 over x. To make this look like that, I just have to multiply by x squared. And if you multiply the middle by x squared, then you're going to have to multiply the outsides by x squared. Everybody okay algebraically? All right, look what we have. We have now our ugly function trapped between two nice functions. And by nice functions, I'm meaning, can you find the limit as x approaches anything of -x squared? Yeah, you could plug in any number into that, so we're good to go. But we still need to work through this limit part, so here's what we show. The limit as x approaches, all right, look back at your original problem up here. We wanted to approach 0, so the limit as x approaches 0 of -x squared, that's 0. And the limit on this other nice one as x approaches 0 of x squared, that's also equal to 0. Since the limit as x approaches 0 of our two nice functions was 0, and this ugly one is fitting in between, therefore, you guys know this triangle, 3 dots, therefore, the limit as x approaches 0 of x squared sine 1 over x is also 0 by the sandwich theorem. Okay? You pretty much kind of have to start off, you're going to start with a trig function, and you're going to start it off between -1 and 1. It's going to be a sine or a cosine. And then you're going to do some mathematical procedures to generate that ugly function. And then you're going to get down to two nice ones. These two nice ones have to have the same limit. If they don't, you did something wrong. They have to come up this way. Does that make sense? Is it the juniors that are normally so talkative, or are you guys afraid of being on tape? Nobody says anything still. That's a riot. Okay. Let's move on. All right, we'll start section 2.2 today. You are going to need a calculator. Please go ahead and fill out your calculator. Do you need to borrow a calculator? Do you have one? Yeah. Oh, go get it then. Anybody else need to borrow a calculator today? You want to borrow a calculator? Okay, so go ahead. We're going to look at some limits today. This one first. The limit as x approaches 5 from the left of 1 over x minus 5. So I want you to pull up the graph. Go ahead and graph that. Depending on your window, the graph might be a little bit flatter than this, but you should see something come up like that. We have an asymptote at x equals 5, a vertical asymptote at x equals 5. Everybody agree? Off your calculator? Yes? No? Maybe? Yeah? Okay, perfect. Alright, so now, sketch this into your notes, because we're going to have to talk about a couple of things here. Alright, looking at this limit as x approaches 5 from the left. So coming at 5 from the left-hand side, what are your y values doing? What are your y values doing as we come toward 5 from the left-hand side? Where are they going? Down, bigger and bigger and bigger, more and more negative? Okay, we say that they are heading toward negative infinity. Now again, negative infinity is not a number, it's a concept. They are not heading toward any one particular number. What this means when we say a limit has a value of negative infinity, we are saying or meaning that the y values of the function are decreasing without bound. So there's no stopping, no ending point here. They're going to keep going down farther and farther and farther the closer and closer and closer we get to 5. Okay, what about x coming toward 5 from the right-hand side? X coming toward 5 from the right. Now what can you tell me about your y values? They are going toward positive infinity. And can you describe that? Brad, can you describe it? In terms of this, instead of the y values of the function are decreasing, they're going to be increasing. Exactly. The y values are increasing without bound. Okay, from these two together, the limit from the left side of 5 versus the limit from the right side of 5, what can you tell me about the limit as x approaches 5 in general of 1 over x minus 5? Are they going the same direction? No, one's going up, one's going down, so this limit does not exist. Okay, so far? All right, look at this next one. Go ahead, type this one up in your calculator. And then we're going to sketch that graph as well. Morning. Okay. All right, you can't tell from the graph that looks on your screen because your windows kind of is too big, but we're going to greatly enlarge this. I think we all can agree with that piece here. All right, this piece on the other side, it comes up this way. It's going to hit up here right at 2, I believe, when x is 0. Yeah, this is at 2. And it's also, it does cross through the x-axis at x is -2. And that makes sense because if you plug a -2 into this function, the numerator is 0. So when x is -2, this graph does cross through the x-axis. Okay? And you guys don't know how to figure this out yet, but I'm going to tell you that this graph drops down here and it curves back up and it flattens off this way. Without changing that window quite a bit, you wouldn't see that, because I think yours kind of just comes down on the graph, and doesn't it kind of just stop right here at -2? It's very, very close to the x-axis in here, but it in fact does do that. Okay. Now let's find these limits. What's this limit? The limit as x approaches 1 from the left. This vertical asymptote's happening right here at x equals 1. Approaching 1 from the left. Nick, where are they going? Positive infinity, yeah. How about the limit as x approaches 1 from the right? Maddie, what's that one? Also positive infinity. Now, what's the limit as x approaches 1 in general of this particular function? Everybody? Positive infinity. This one, from both sides, both sides are going in the same direction, so we can say positive infinity here. This one, from up above, one was going up, one was going down. The limit does not exist, not going in the same direction. Okay? All right, now, looking back at these last two problems, vertical asymptotes here and here. Notice the limit information that's there. Vertical asymptotes occur in the graph of a function at x equals a when the limit as x approaches a from the left of f of x equals positive or negative infinity, or the limit as x approaches a from the right side equals positive or negative infinity. This is an or situation. Both cases are not necessary. All that's necessary for a vertical asymptote is 1. For example, you could have something that looks like this. In that graph, there is a vertical asymptote at that particular value, whatever it is. There's also a point there. It's only a vertical asymptote, though, coming from the left side of whatever that value is. There's still a vertical asymptote there. It's just only valid from the right. Okay? So far? We good? All right? Now, we explored this initially with your calculator. Now we're going to go through and we're going to analytically, so without a graph, without your calculator, find each limit. from the last couple of days here, what's the very first thing that you do when you want to evaluate a limit? Katie? Plug in, absolutely. So let's plug this 1 in here. When we plug a 1 in, we're going to get a 3 over 0. Okay? Any time that you end up with this situation, after you've tried to factor, after you've rationalized, yada, 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 if you end up with a non-zero constant in the numerator and a 0 in the denominator, that limit will be positive or negative infinity. You just need to decide which one by doing a sign analysis. Okay, so here you gotta think with me. Coming at 1 from the left, is that a tiny bit bigger than 1 or a tiny bit smaller than 1? Coming at 1 from the left side, is that bigger than 1 or smaller than 1? Smaller than 1. So you're thinking signs now, whether just things are positive or negative. Tiny bit smaller than 1 plus a 2. 0.99999 plus 2. Is it positive or is it negative? Positive. Something smaller than 1. 1 minus something smaller than 1. So 1 minus 0.999999. Is it positive or is it negative? Positive. You have positive over positive. Overall, positive infinity. Okay. Let's look at the next one. Same function here. When we sub in, we were going to get that non-zero constant over 0. So that leads us to a plus or minus infinity. And let's do our sign analysis. Coming at 1 from the right, that's a tiny bit bigger than 1, like 1.00002. 1.00002 plus a 2 is positive. 1 minus 1.00002, negative. Positive divided by negative, negative infinity. Okay, so that's the analytic part of it. And the big deal is you have to look for a non-zero constant over 0. Anytime you get this situation, the limit will be positive or negative infinity. All right, here we go. For f of x is x minus 4 over x squared minus 16. I want you to find all of these limits, then use this information to sketch a graph. Okay? All right, as you're starting, what are you seeing right off the bat when you're looking at this x minus 4 over x squared minus 16? Factor, absolutely. So we have x minus 4 over x plus 4 times x minus 4. And the x minus 4's divide out. We're left with 1 over x plus 4. Okay, let's find all these limits. The limit as x approaches negative 4 from the left side. The limit as x approaches negative 4 from the right. The limit as x approaches 4 from the left. And the limit as x approaches 4 from the right. Okay, when you sub in, if you go back into this original one, you're going to get a 0 in the denominator. So you're going to want to go through the factoring, which we did. Now sub in again. So sub into this simplified form. The limit as x approaches negative 4 from the left. We put a negative 4 in here, and we get 1 over 0. Nod your heads, yeah? Okay, which means then we need to do that sign analysis. So Boy, the negative 4 from the left-hand side. That's a little bit more negative than negative 4? Like negative 4.0002? Okay, put that up here. 1, oh, tell me about the numerator in terms of sign. Always positive. Denominator, a little bit more negative than negative 4 plus a 4. That's negative. So this limit then is going to negative infinity. Put in a negative 4 from the right. Same thing, you're still going to get that 1 over 0 situation, doing a sign analysis this time. Negative 4 from the right is like negative 3.99999. So negative 3.99999 plus a 4, positive. So this is positive infinity. Okay, right here. As soon as you do the limit as x approaches a particular number and it comes up with positive or negative infinity, this is telling you that you have a vertical asymptote. At x equals negative 4. Okay. All right, how about this one? The limit as x approaches 4 from the left. 4 from the left. Plug in to the simplified form and we're going to get 1/8. Same thing coming at 4 from the right. 1/8. But what's f of 4? F of 4 is not 1/8. Go back to the original function, plug in a 4. Well, it's 0 over 0, right? 0 over 0 doesn't exist. You're not allowed to sub in x equals 4 into that original function. So there is no point plotted there. The limit exists, but there is no point. That's telling you there's a hole at 4, 1/8. Okay. Before we sketch this, let's find a few more pieces of information. Let's find x-intercepts and y-intercepts. X-intercept happens when y is equal to 0. When this function is equal to 0. Can this ever equal 0? Nuh-uh, because the only way a fraction can equal 0 is if the numerator is equal to 0. That numerator will never equal 0, so there aren't any. Never, ever, ever crosses or touches the x-axis. Y-intercept happens when x is equal to 0. So we're going to plug in x equals 0. And you can go either to the original or to the simplified form, doesn't matter. What do you get? 1/4, yep. Okay? Andrew, okay? You look puzzled. Good? All right, let's sketch this graph. Use a ruler and mark off your graph as accurately as possible. We've got quite a bit of space here. I'm measuring off in centimeters. right, here we go. We had a vertical asymptote at x equals -4. Vertical asymptote at x equals -4. We have a hole at 4, 1/8. It's hard to get that hole down small enough to show that it's 1/8. So just identify the coordinates of it. No x-intercepts. Y-intercept is 0, 1/4. 0, 1/4. And that's all we've got. But we can use these limits. The limit as x approaches, I'm going to look at this -4 from the left first. As x approaches -4 from the left, the y values go toward negative infinity. They decrease without bound. So here's -4. Coming at -4 from the left-hand side, the y values have to decrease. They have to get smaller. So it's got to do something like this. They have to go down. Now, I couldn't have drawn it up here. Look up here so you can see what I'm saying. If I draw it up here, then I would have had to have crossed the x-axis. And we know we can't cross the x-axis, so I don't want to draw it up here. Does that make sense? And we know it can't cross the x-axis, so we do know that this has to flatten off over this way. On the other side, on the right side of -4, we know that those y values increase without bound. So as I get closer to -4 from the right-hand side, these y values are getting bigger and bigger and bigger. And we can kind of go and connect these guys up with this y-intercept that we have to hit. And also with this hole over here that we have to hit. Does not cross the x-axis, so just flattens out along here. Are we good? Questions? One more today? Then we'll call it quits? All right, we'll do one more for today, and then we'll call it quits for today. All right, let's look at this one. For f of x is x squared plus 2x minus 3 over x squared plus x minus 6. Find all of these limits. Then use this information to sketch a graph. Oh boy. What do you see? Factor. You're always looking to try and simplify these things in factors. So this is going to factor into, what do you got? Have I got the numerator? Maddie, do you have it? I think you have your signs backwards. Plus 3 and a minus 1. Anybody have the denominator? Sam, do you have that one? I think again you have the signs backwards. X plus 3, x minus 2. Hey, what happens? X plus 3's divide out, and we're left with x minus 1 over x minus 2. All right, so let's go find these limits. How about this one? The limit as x approaches -3 from the left. Sub in. -3 up here is going to be a -4 over -5, which is 4/5. How about -3 from the right? This going to be the same thing? Yeah? Okay, is this function defined when x is equal to -3? No, because they canceled out, right? Do you remember? What does this tell you? There's a hole at, what's the x coordinate of the hole? -3, and the y coordinate? 4/5, because that's the limit. That's what things are getting close to when we get close to -3. Okay, how about a limit as x approaches 2 from the left? Plug in a 2, and we get 1/0. Non-zero constant over 0. It's telling you positive or negative infinity. So 2 from the left, tiny bit smaller than 2, like 1.9999. 1.9999 minus 1. Positive or negative? Positive. 1.99999 minus 2. Negative. So this limit, negative infinity. X approaches 2 from the right, tiny bit bigger than 2. We're going to get a positive over positive this time, so this one's going toward positive infinity. What is this telling you that shows up in your graph? What kind of asymptote, Emmer? Vertical, yeah. At x equals 2. Okay, a few more pieces of information that are going to help us sketch this graph. The x-intercept. X-intercept happens when y is equal to 0. Look at this simplified form. Could this ever equal 0? Yes. The way a fraction can equal 0 is if the numerator is equal to 0. Can this numerator ever equal 0? Yeah, it will when x is 1. So that's going to happen when x is 1. So the ordered pair then is 1, 0. The y-intercept happens when x is 0. Plug in x is 0. And we'll get a half. Okay? All right, let's sketch. Here we go. We have a hole at -3, 4/5. -3, 4/5 is right about there. There is a vertical asymptote at x equals 2. We have an x-intercept at 1, 0. And we have a y-intercept at 0, 1/2. Okay, I'm going to give you another piece of information that we talked about earlier this year. We've actually talked about all these asymptotes and holes and stuff earlier this year. We just did it pre-calculus way. Now we're doing it calculus way. There's a horizontal asymptote here at y equals 1. We've talked about that before pre-calculus. We haven't talked about that horizontal asymptote yet, calculus way. All right, very definitely you can kind of see these 3 points connecting up. Let's just verify that that matches our limit information. As x approaches 2 from the left, negative infinity. Absolutely, that's working. Okay, 2 from the right, going toward positive infinity, which means we need to have this piece up here. Okay, don't pack up yet. I just want like a minute more of your time. I just want to draw this together with what we did first semester. Do you remember graphing these things first semester? Yeah, and do you remember how we didn't do all this limit stuff to come up with holes and all this vertical asymptote stuff? Do you remember how we did it? How? Absolutely. If there was a factor that canceled out, then there was a hole at that particular point. And if we had a factor that did not cancel out, then that generated a vertical asymptote. Do you remember that, Andrew? Right now, I'm just telling it to you. Okay, we're going to actually talk about that tomorrow. So right now, just go with it, that I'm telling it to you, and then we'll clean up. I'll go back over again from pre-calculus and then the calculus way to determine that that's a horizontal asymptote there. Tomorrow, we'll pick that up tomorrow. No, we won't. We'll pick it up Monday. All right? Okay, you guys, have a nice weekend. We are caught up. Yes. So, homework-wise, you should be able to get through section 2.2 day 1. 2.2 day 1 at this point.